Okay, our next talk is by Chris Helmerson.
Great. Okay, well, let me start by thanking the organizers for the opportunity to come out and talk about some experiments, actually, that are going on with ultracold atoms at Monash University. We're located in Melbourne, Australia. So here's a brief outline. Oops, I'm not sure. There we go. So here's a brief outline what I'm going to talk about. Since Professor Berenghi gave a very nice introduction to quantum turbulence, I'll probably quickly go through a lot of the background information, just setting the stage for things. What I'd really like to focus on, because my experiments are focusing on studying two-dimensional turbulence, and so I want to show how 2D differs remarkably from 3D. And then I'll talk about a very important model of 2D turbulence, Onsager's model, and then a little bit about some of the simulations we've done on that, and then I'll go into the experiments. All right, so don't have to sell this crowd why turbulence is important. But let me just move on and talk about some aspects of turbulence, okay? So we have this thing called an inertial range where we can have energy transfer without dissipation. And there was a mechanism proposed by Richardson, and it involves a cascade of energy. Basically, you inject energy at some length scales, you form vortices at that length scale, and they break up into smaller and smaller vortices until, this pointer here, until eventually you get down to a length scale where dissipation can take place. And so this provides basically a phenomenological description of how turbulence evolves over different length scales. Now, there are not very many statistical models of turbulence. One of the most famous one is Kolmogorov's model, which predicts basically that you can have sort of isotropic and homogeneous turbulence, and you have this cascade process becomes very self-similar, and so you can predict scaling laws. Now, I want to move on to two-dimensional turbulence. So there are many examples in physics where changing the dimensionality of the system can lead to remarkably different behavior. One example of this is, of course, Bose-Einstein condensate, a field I work in. There's no BEC in a two-dimensional system, certainly an infinite two-dimensional system, but there's superfluidity due to the Berezinski-Kosterlitz-Thouless transition. You can also have quite different behavior of turbulence in two dimensions. And it's interesting and unusual. And there's lots of examples of 2D flow. Atmospheric flow can be modeled as two-dimensional flow because the atmosphere is thin compared to its extent. Certainly in ocean situations, you can have stratified flow where it's described by as two-dimensional flow. What you find happening in two-dimensional turbulence is the formation of large-scale vortex structures. And this can be observed in systems ranging from soap films up to atmospheric-sized systems like the giant red spot on Jupiter is sort of a classic example of this. And this is, in fact, due to what's called an inverse energy cascade. So whereas before we had the regular energy cascade of vortices, injection at some length scale, breaking up into smaller and smaller vortices until dissipation can take place. In two-dimensional turbulence, you can actually have the inverse process happen. So you inject energy at some length scales, it can actually build up into larger and larger length scales. And so you can have large-scale vortex structures. So if you look at the energy spectrum, okay, you have the traditional energy cascade down to smaller and smaller length scales, larger and larger wave vectors. But you can also have the inverse process where you actually build up going to large length scales or small wave vectors. And Onsager first noticed that this was an unusual feature of two-dimensional flow, that you can have this large vortex structure forming in systems. And so he proposed a statistical mechanics model based on, to explain basically the appearance of these large-scale vortex structures. And in Onsager's model, he actually predicted what are negative absolute temperature states in the system. And also, yeah, so that's basically what he predicted in his model. Now, in his model, basically, he had to approximate vortices in the system as point-like particles. And so, strictly speaking, this model is really only applicable to superfluids, and Onsager noticed that and commented on that. In addition, this is the famous paper in 1949 where he actually predicted, or basically stated, that vortices in a superfluid are quantized. So So I think this is the first reference to quantized vortices in superfluids. But in this model, well, so let's go on to superfluid turbulence, okay? So we've already heard from Professor Berengi that basically in superfluid, we have quantized vortices in the system. A possible mechanism for this energy cascade was proposed by Feynman, where you can have vortex rings, okay? And through a process of reconnection, they can break up into smaller and smaller rings. And so this leads to a sort of a vortex tangle in the system. All right. Now, Onsager's point vortex model is essentially the same model you would use for point charges in a two-dimensional system. So if you had positive and negative charges in a two-dimensional system, they would interact via this sort of logarithmic type interaction. So it's a model that goes all the way back to Helmholtz for describing the behavior of point charges in the two-dimensional system. But basically using this model, Onsager basically predicted that what happens in this system as you put energy into this system is that the energy has to be taken up by the flow field, and this corresponds to these point-like vortices basically clustering so that you have clusters of one sign vortices and clusters of the other sign of vortices. And according to Onsager, this basically corresponds to negative absolute temperature states. So let me just briefly explain what I mean by negative absolute temperature states. Well, first of all, negative temperatures are fully compatible with thermodynamics, okay? And the requirements to have negative temperature states in statistical mechanics is first, you need the system to be described by temperature, okay? So it has to be in some sort of equilibrium or quasi-equilibrium where you can describe it by a temperature. There has to be an upper limit on the phase space of the system. So basically, it only corresponds to systems that have a finite phase space. And finally, the system has to be thermally isolated from non-negative temperature states, okay? Because negative temperature states correspond to high energy states. And so as a result, you can have energy going into the other system if you have a non-negative temperature state. And one of the first people to actually apply the concept of negative temperatures to experiments were the people doing NMR experiments, people like Purcell and Ramsey, okay? And so I find a convenient model for explaining negative temperatures. It's basically based on spin. So imagine you have a spin-a-half system, you have ground state, and you have a spin-up excited state, okay? At zero temperature, you'd expect all the spins to be in the lowest energy state, ground state. Now, as you start putting energy into the system, okay, then you start putting some of the spins into the upper state. And at some point, you have basically an equal distribution of spin up and spin down, but sort of randomly distributed between spin up and spin down. And so that corresponds to the maximum entropy state of the system, okay? But because you have a finite number of spins in the system, as you start pumping more energy into the system, you start putting more and more of the spins into the excited state here, okay? And when you do that, then you start decreasing the entropy of the system. The entropy starts going down as you start putting more energy into it. Now, if you want to describe this by a Boltzmann-type distribution, then this basically would correspond to having negative absolute temperatures. And so this is what I mean by essentially negative absolute temperature states. So it's a low entropy, high energy state, okay? Negative absolute temperature states have been observed with atoms, for example, atoms in optical lattices in Emmanuel Bloch's group. But we're actually going to be looking at negative absolute temperature states and vortex distributions, which are actually driven by the interactions of the atoms. With this picture of negative absolute temperature, this energy versus entropy type distribution, we can actually come up with a generic picture of the finite 2D Bose gas based on this. And so this is our picture of the finite 2D Bose gas. So at zero temperature, we essentially have, for this finite system, we have a Bose-Einstein condensate. So you can actually have a Bose-Einstein condensate in 2 dimensions for a finite system, all right? So we have our finite Bose-Einstein condensate here at zero temperatures. As we put energy in, we have this, we start generating excitations in the system in the form of vortex-anti-vortex pairs. As you put more energy in, these vortices and anti-vortices break apart. And eventually you reach sort of a maximum entropy state where you have a sort of a random collection of vortices and anti-vortices in the system, all right? And so this way we'd say corresponds to essentially being at infinite temperature. Now, as you start putting more energy into the system, you basically have to come up with an arrangement of the vortices and anti-vortices that can take up the extra energy, all right? And the way they do this is they cluster together so that basically the energy goes into the large-scale fluid flow motion. So that's what this corresponds to here. You have sort of large-scale fluid flow in the system, and that's how the energy gets taken up. And eventually you can put enough energy into the system where it's predicted that these vortices, these clusters of vortices should condense into multi-charged vortices.
What is OV standing for?
Onstarter vortices. So we call this cluster state, we call them onstarter vortices. So that's what OV stands for. All right. So we've done some simulations. Tapio and Matt Davis have done some simulations of using the Gross-Pidievsky equation. In this simulation, basically, they start with an equal number of vortices and anti-vortices. So they start with a total of 40 vortices and anti-vortices imprinted onto a Bose-Einstein condensate. It's in a flat-shaped potential, and it's in a circular boundary. Okay. And so blue is rotating one way, green is rotating the other way. And initially, these 40 vortices start, the vortex-anti-vortex pair come together, they annihilate. But after a while, you start seeing sort of a clustered behavior. And this white line here corresponds to the dipole moment of the system. So it's basically an average over the distance between the vortices and including their charge, the sign of the vortices. And so at some point, you sort of see this clustering behavior of these vortices and anti-vortices in this system. All right. Now, in this picture I showed you of the entropy versus energy here, I said that if you wanted to transition from this sort of disordered state, sort of a random collection, to a state where you see clustering of the vortices, you had to basically put energy into this system. Yet the simulation I just showed you was basically a closed system. We didn't actually pump energy. You started with a certain configuration of vortices, and then you just let the system evolve, okay? So it's a closed system. And so one of the questions you might have is how are you actually putting energy? You start seeing clustering towards the end, okay? And so how are you going from this initial random distribution of vortices and anti-vortices to this clustered state, right? So we observed sort of this, coming from this sort of random distribution, we observed this more ordered state of onstarter vortices. And the mechanism we proposed for this is something we call evaporative heating, okay? So when you have a vortex and anti-vortex, and if they're fairly far apart, they have a flow field associated with them, okay? But as you bring them closer and closer together, the net flow field around this is basically zero. The flow field's canceled. So when you have two vortices, a vortex and an anti-vortex pair close to each other, then it basically corresponds to a low energy flow state, because there's not much of a flow field around the pair of vortices. And so this annihilation process is basically removing pairs of vortices, vortex and anti-vortices, that correspond to a small flow field or low energy state of the system, okay? And so as a result, when that happens, the remaining energy of the system has to get redistributed among the remaining vortices. And so the average energy per vortex actually goes up in that process. So this process of removing the vortices and anti-vortices, which we call evaporation, actually leads to heating in this case. And you can simulate this using a point vortex model to show that it's in fact just basically due to the incompressible energy of the system, just the flow field of the system. And so here's a point vortex simulation. In this point vortex simulation, though, what we do is we get my cursor back here. Maybe it's this way. No, I can do that. All right. So in this point vortex model, we have, in this case, 40 plus vortices and 40 minus vortices. But in this point vortex model, we actually put in by hand annihilation. So when a vortex and anti-vortex come within a certain distance of each other, we actually remove them from the system. So we built annihilation into this point vortex model. And you can see that basically you get the same behavior as the Gross-Pidievsky equation. After a while, you start seeing clustering of vortices, right? And so based on the point vortex model, I mean, you see the number of vortices decay over time, but you can also compute what the average energy is per vortex is, and in fact, you see that increasing. So this suggests that well, first of all, it suggests that the annihilation process is important for this to occur. And in fact, we think it's basically due to this vortex heating mechanism. All right. So we can classify the vortices in this system, okay, based on their whether they actually belong to a pair of dipoles or whether they belong to a cluster. And we use a scheme that was proposed by Matt Reeves, who's here, and his collaborators, slightly modified by Tapio and Rahil Valani and Andrew Groshek, who's also here. But basically, the idea is that you start with a vortex somewhere, okay, and you find the nearest vortex, the closest vortex to it, and you identify whether it's plus or has the same sign or the opposite sign. And then you take that vortex and you look to see where its nearest neighbor is. If it's the same one, then you classify it as a dipole if it has opposite sign, or you classify it as a cluster if it's of the same size. And you do this for all the vortices, and then whatever's left at the end, you just classify as a free vortex. All right, so the remaining vortices then are just classified as free vortices in the system here. Okay? But based on that, it turns out that you can actually assign a temperature to the vortex distribution. So Andrew and with others has basically done Monte Carlo simulations for various temperatures of the equilibrium vortex distributions. And what they find is that there's actually a monotonic behavior of the fraction of clustered vortices and dipole vortices as a function of temperature of the vortex distribution. And this means that we can actually use it as a thermometer for assigning a temperature to a particular vortex distribution. So in other words, if you know the fraction that belong to a cluster, the fraction of vortices that belong to dipoles, then you can assign a unique temperature to the vortex distribution. All right. You can also, based on the gross, either the Gross-Pedievsky equation simulations or the point vortex model, generate basically the energy spectrum. And you can see that, in fact, as the system evolves into this clustered state, you get a buildup of energy at the small length scales. The large length scales or the small wave vectors. All right. So let me move on to the actual experiments. Yeah. This is, I think this was, in our case, it was for the actual simulations where things are just going by evaporative heating.
Because something in the universal scale shows that it's infinite capacity.
Yeah.
So basically, in order to build up the cascade, you need to inject energy. Otherwise, it doesn't
Right.
work. So here it's just decaying.
Yeah, it's sort of a decaying turbulence, but it's still, I think it still evolves into this shape. And I'll show you some spectra taken from the experiment that look like this. All right, so for the experiments, well, first of all, we find that it's important to have this sort of flat bottom potential. Andrew had done some simulations based on power law shaped potentials. So potentials that go like some R to the some power. And so here's the case between having a harmonic, so R squared type radial potential versus R to the 100 potential. And so if you let the system evolve in these Gross-Pedievsky equation simulations, you see a very small net dipole moment in the harmonic potential. But if you go to this effectively flat bottom potential, you can see clustering of these vortices. Okay? So that's one requirement for the experiment, is that we need a fairly flat bottom trap, okay, as opposed to a harmonic trap. And so experimentally, we create this flat bottom trap by first confining the atomic cloud, the ultracold atom cloud, or this Bose-Einstein condensate, in a very flat potential, or we squish it down in one dimension, by confining it in, well, we confine everything with light beams, okay, with optical potentials. But we confine it in this HG01 mode, okay? And so we squeeze the cloud down. So it's confined in this node of this HG01 mode in the dark line in between, okay? And so it's very, very flat. And then we impose a radial potential wall that's fairly sharp, okay? Probably something like R to the 12th, okay? And we do this by projecting a ring of light using a spatial light modulator, so using sorry, a DMD, a digital micromirror device. We create a ring-shaped light, beam of light, which we project perpendicular to this other direction. Okay, and so this creates this sort of ring-shaped potential here, okay? And so this is the confining potential of our trap. It's fairly flat bottom. We do have to weaken this axial trapping mode here, this HG01 mode, to get it to be as smooth as possible, as flat as possible. But we can levitate our atoms against gravity so they don't fall down because they're in a magnetically sensitive trap state. All right, so the next thing we want to do is actually generate some sort of turbulence or excitations in the thing. And what we do is we basically drag optical barriers through the cloud of atoms, okay? And so if you drag an optical barrier through a cloud of atoms, in the wake, you generate vortex, anti-vortex pairs. And we sort of modeling based, on grid-type experiments in superfluid helium, we create basically a grid of barriers that we sweep through the cloud. So here we have a grid of optical barriers that we're sweeping through. And we do this by basically projecting a sequence of images with our digital micromirror device. In our case, we actually have two grids moving in opposite directions so that we don't create some sort of net flow in the system. So we drag two barriers through. And after you do this and take a picture of the distribution of atoms in the cloud, you can see the generation of vortices in the system, okay? And so the vortices, the vortices, initially we generate roughly maybe 40, somewhere between 20 and 40 vortices. They decay down, but if you look at the net polarization, the number of vortices and anti-vortices, that stays pretty constant. Which brings me to the next point, okay? We need to detect the flow pattern in the cloud. So here I've just shown you that we can generate vortices in the system, but to actually know what the flow field is in the system, we actually have to know the sign of these vortices. We have to know whether they're rotating clockwise or anti-clockwise. Once we know the sign of the vortices, then essentially we have a map of the flow field of the system. And so to detect the flow field of the vortices, basically, well, first of all, we can detect the location of the vortices. That's pretty easy just by doing this absorption imaging of the cloud of atoms. You can see holes in there. And we use this is in time of flight, yeah. And then we basically use a blob detection or an algorithm to find the holes in the cloud that was developed by Simon Cornish's group in Durham, okay? We also do some visual inspection to make sure that things are matching up. But the most important thing is we want to detect the sign of circulation, okay? So we want to know whether the vortex is rotating clockwise or anti-clockwise. And to do this, we use a technique called Bragg, well, we call it in the field Bragg diffraction, but it's basically a photon scattering technique that has a Doppler sensitivity associated with it. So it's a two-photon scattering technique where you send a laser beam from one direction, a laser beam from the other direction, and there's a frequency detuning between the two laser beams. So what happens is the atom will absorb a photon from one beam, be stimulated to emit a photon in the other beam, and during that process, it gets a momentum transfer of two times the photon momentum to the atoms. But if you by adjusting the detuning, you can also make it Doppler sensitive, okay? So you can make it sensitive to the initial velocity of the atoms. And others have used this. For example, Chandra Raman's used it to detect the rotation of a cloud, which has vortex lattices in them. Okay, just an example of using it when I was back at NIST, where we actually generated a vortex state and a BEC, and we can use this to actually map out the flow velocity around it by just varying the detuning. Okay. So what happens in this situation is, depending on one detuning, you'll interact with atoms with moving one direction. So if this is rotating clockwise, then you'll interact, for example, let's say the atom's moving off to the left here, and so that portion of the atoms gets kicked by these two beams. If you change the detuning to the opposite sign, then you interact with the atoms that are moving in the other direction, so the top of the cloud gets kicked out. And so this technique was actually introduced or developed by Young-Il Shin's group in Korea, who used it to actually identify the sign of the vortices in this Bose-Einstein condensate. And so basically you use two sets of beams, okay? And so the two sets of beams with the detuning means that if you have a vortex rotating here, one set of beams will kick atoms out from moving in one direction, and the other set of beams will kick atoms out, moving in the other direction. And so when you apply these two sets of beams to your cloud of atoms, you get a cloud being kicked out over here and a cloud being kicked out over here. So this is in time of flight after this cloud has 2h bar k of momentum transfer, this has minus 2h bar k of momentum transfer. So they separate out after some time, and you get an image like this. And then what they do is they color one of the clouds blue and the other one's red and superimpose them. And basically, by looking to see whether you have a transition going from red to blue or from blue to red, you can identify that as a vortex rotating clockwise or anti-clockwise. Okay? So we use this technique, but we actually, so we use this technique to find the, to measure the velocity field. We identify the location of the vortices from the absorption image here, okay? And so that's what these X's are. But then what we want to do is compare that to a point vortex model. So we basically generate a point vortex model with the location of the vortices in the point vortex model given by the X's here. And then we sort of randomly assign signs to the vortices in the point vortex model. And we find the configuration of point vortex the point vortex model that maps onto the actual image here. And we say that's the configuration that we have. And then from that, we can identify whether clusters or free vortices or dipoles. And so here are three different situations. This is a regime where we have mainly dipoles. This is a regime where we have sort of random number of dipoles and clusters. And here's a regime where we're in the clustered regime. And so once we have that, then we can assign a temperature to the cloud using the same technique, okay? I don't want to go into too much detail here, but we can basically put different distributions. So each one of these sets of vertical data points correspond to some configuration of the experiment, whether basically the grid spacing and also the amount of time that they're held in the trap, okay? I think I'm running out of time, so let me just skip over the details about how we do this, but just show you some results, okay? So here's some results where we change the size of the grid, okay? So here's basically different grid sizes, okay? And so we can see in this situation when we go to large grid sizes, we generate clouds of distribution of vortices that have a negative temperature. When you go to small grid sizes, you have something that's close to zero temperature, or basically this sort of random distribution of vortices. And we can confirm that with a number of things, like looking at the dipole moment of the system. We can look at basically the first order correlation function to see whether the nearest vortex is positive or negative, and so on, okay? Also, once we have the point vortex model for that particular configuration, we can actually look at what the energy spectrum is, okay? And you can see that in the case where we go to this large grid spacing, we get a large build, the kinetic energy spectrum shows this peak at large length scales or small wave vectors. All right. We also have some evidence of this evaporative heating, okay? So here's a situation where we just focused in on going with this particular grid spacing, 6 micron grid spacing. And we can see in this case, we just look at it as a function of hold time, and we can see the system. Oh, sorry.
The grid spectrum is from the experimental data?
No, this is from the point vortex model, which looks like the experimental data. Psi is the healing, it's the vortex core size, yeah.
The meaning scale is smaller.
You mean out here?
On the right.
I don't know, Andrew might know. Yeah, I think he generated these. Yeah. Yeah, we're basically just concentrating over here. This is the scale at which we inject the excitation. And so we were mainly looking to see whether we get a buildup at large scale. Oops, uh-oh. Did I run out of time? Okay, I seem to have, I hit forward and it seemed to have quit. So,
Oh, we probably exited your display.
no, I just hit forward, but let's go back to PowerPoint. Oh, the whole thing crashed.
PowerPoint crashed.
Yeah. That's right. All right. Ignore slideshow. Let me just play it here, explain what's going on. All right. Right, so this was for a 6-micron grid size. Like I said, we see some evidence of evaporative heating here, where we go as a function of the amount of time. So we initially generate the distribution of vortices in the system, but over time we evolve to a negative temperature over here, okay? And also the average energy per vortex is actually increasing as a function of time, all right? We can also look at the how this evolves, also in terms of the energy spectrum, and we also see some evidence of sort of the system going from initial along a particular fixed point to a thermal fixed point. So starting at a non-thermal fixed point, we're corresponding to this clustered state, and going to a other fixed point. So I think I'm out of time. Okay, all right. Here's a situation where we actually look at a larger grid spacing, in which case we generate mainly a clustered distribution, so the system doesn't evolve. In fact, if anything, we see a decaying of this clustered state as a function of time. All right, just skip over that. So I just want to advertise that also there's experiments being done at University of Queensland, and Tyler will talk about that after lunch, where they go well into this negative temperature state, so this highly clustered state. So I'll skip over the conclusions, but I just want to basically mention the people involved in the experiment. So these experiments are only possible because we had very strong theoretical support by Tapio, Matt Davis, David Paganin, but mainly Andrew did most of the hard work on this, mainly for his PhD thesis. And on the experimental side, Sean Johnson, for his PhD thesis, had done most of the experimental work. So let me just end here, and thanks. Here's Tapio miniaturized to study microdynamics.
Great. Thank you very much. Any more questions before lunch? Oral?
It's a kind of a general question here. So you touch upon two aspects here. For example, the entropy.
Yeah.
She has this behavior and temperature increases. But the way you define entropy and energy there is not the usual thing which is done in thermodynamics. Your quantities are not extensive, they're intensive. So you have energy per vortex, you have entropy per vortex. In thermodynamics, we discuss typically quantities which are extensive. Mm-hmm. So for that reason, you see that this is a bit, I don't know, I feel a bit uncomfortable with this. I cannot exactly describe where what's wrong with that. The other thing is you have a basically closed system.
Yeah.
You should reach an equilibrium. And when you reach an equilibrium, entropy should increase, but not decrease. But this is what happens.
Yeah.
See, and you don't do that. And then you mentioned another term, the evaporative heating, which is opposite to what we are used to, evaporative cooling.
Yeah.
And probably you refer to the previous state, which the energy actually per vortex increases. See, this is what we call property.
Yeah.
So it's not actually evaporative, it's simply the energy of the cluster system is increasing.
Well, I would say
it's dumping to the rest of the system or something like that.
Right.
So I don't know. You see, my question is, it's actually 3 of them or so, something like this.
Yeah. No, I can understand your discomfort with maybe. I mean, part of it's semantics. I mean, what you want to call evaporation. I mean,
yeah,
because
I agree with that.
Because vortices are leaving the system. But yeah. Well, we are dealing with a finite size system, so I mean, whether.
But you're not dealing with extensive quantities, you're describing intensive quantities. And this is the difference is huge. Totally unusual.
Yeah, but I don't think so. I think the way I.
There's also a condensation on a microcanonical.
I'm sorry?
Also a condensation on a microcanonical. It's all this consideration of negative and positive temperatures, a fixed number of vortices. So
total energy is conserved.
Hmm?
Total energy is conserved in the system.
Yes.
Yes, also a number of
But here it talks about energy of a subsystem.
That's true. I decouple the vortex system from like sound. Okay, so you do have sound being generated, and eventually everything will thermalize, right? If you wait long enough. But on the time scale of the experiments, it's sort of in quasi-equilibrium. This vortex system.
Something about that. What you do for like a statistical thermodynamics, because you do thermodynamics of gases, you still deal with particles.
Yes.
So your vortices like molecules in statistical thermodynamics.
Yeah.
So I don't think that this was great.
Yeah.
I'm sorry.
So I think these vortices, let's say you have point vortices, and they're like analogs of molecules in statistical thermodynamics. So it just does exactly the statistical thermodynamic argument for vortices with a particular type of interaction between vortices that comes out from the surrounding interaction.
I don't quite agree with you.
So it does not apply to the,
Yeah.
it does not apply to the VC itself.
No, no, no.
So this is
It's
really
just the vortices.
statistics
Yeah, I'm just
of the
looking at the
vortex and
this-
vortex
this-
distribution in this box.
Right.
So it's an extensive.
Any-
Just a quick question. How do you identify the unpaired vortices?
The unpaired.
Yeah, because with your nice track technique, you can find the one that are positive or negative by the signature. But the remaining ones, how do you detect them in the experiment? Just like the holes?
Yeah, the holes, and then
no
with
attributes.
so every hole seems to have, well, because of the Bragg scattering, we have some measurement of the velocity field associated with that. The only ambiguity comes when you have like a vortex, anti-vortex close to each other, then essentially there's no net flow around it. And so we kind of identify that as possibly a vortex or anti-vortex pair. If we really can't definitively say anything about it, we don't actually use that data. So we just throw it out.
So your total number of vortex, is it conserved within this noise, residual noise, or not?
The total number of vortices?
Yeah.
So if I look at the number of holes and identify, yeah, if it's not, we don't actually use it.
Okay.
One final
Yeah.
question.
It's a pretty quick question. You were saying that your results depend on whether you have a fine or a wide grid.
Yeah.
So which is the length scale I should be comparing to define?
So the fine grid basically generates a random distribution of vortices, because it basically generates a bunch of dipoles, because every one vortex on one side will generate the opposite side from the other grid next to it. When you go to a very big grid spacing, then you can generate large scale flow, and that corresponds to generating large clusters.
When I'm thinking large, so small one, I should be thinking of the dimensions of this one.
Yeah, I mean, the grid size varies from 4.3 up to something like 11 microns. So it's certainly large compared to the whole thing's about 75 microns, something like that. Yes.
Okay, thank you very much.
Okay.